on the ones that you have done. So the mean, how do we find mean? All right, so we add them all up and divide by the number. So 17 plus 9 is 26, plus 13 is 39, plus 15 is 54, plus 26 is 80, divided by how much? 5, which gives us 16. Now we divided by 5 because there's 5 numbers in the list. That is n. N equals 5 is what that means. So that's just saying there are 5 numbers in this list. Now for the median, there are 2 steps we have to do. What is the first step? Put them in order from smallest to largest. So you go 9, 13, 15, 17, 26. Then what do we do? Find the location of the median. So it's going to be n times 0.5 or n times 1/2. Well, n is 5. 5 times 0.5 is 2.5. Now remember, there was 2 cases. If it was a whole number, it was between that spot and the next spot. If it was a decimal, we rounded up. So 2.5 rounds up to 3. It is the number in the 3rd position, which is 15, is our median. Mode. Mode is the number that occurs, or the item that occurs most often. In this set, there is no mode, none. Remember, the mode is actually most useful for categorical or qualitative data, non-numerical data. You can look at it and see which one occurs the most often. Range, how do we do the range? Max minus min, biggest minus smallest. 26 minus 9 is a range of 17. Standard deviation. If you recall, standard deviation was a 6-step process. Step 1 was to find what? The mean. We've already found the mean, it's 16. Step 2 is to subtract the mean from each. So we have 9, 13, 15, 17, and 26. From each of those, we are going to subtract 16. 9 minus 16, negative 7. 13 minus 16, negative 3. 15 minus 16, negative 1. 17 minus 16, 1. 26 minus 16, 10. Now, if we were double checking here, what should those add up to? Should we add up to 0, right? And they do add up to 0 if we were to add them up. That's just a way of double checking to make sure nothing has gone wrong so far. If you recall, those numbers right there were called the deviations. Step 3 is to square each. Now, make sure you keep track of the difference between square and square root. Square means multiplied by itself. So negative 7 squared on your calculator, make sure you put it in parentheses. Negative 7 squared should be positive 49. Anything squared should always be positive. Negative 3 squared, 9. Negative 1 squared, 1. Positive 1 squared, 1. And 10 squared, 100. Those are the squared deviations. Makes sense because we just took the deviations and squared them. What is step 4? Add them up. Find the sum. We add those up and we get 160. That is called the sum of the squared deviations. What is step 5? You divide by n minus 1. Well, we said here that n equals what? The number in the set. So that would be 5 in this case. So n minus 1 is 5 minus 1, or 4, which means we divide by 4. Gives us 40. 40 also has a name. That is the variance, which you might notice is what we're asked to find in number 6. Yes. 1, 2, 3, 4, 5 items in the set. For what? No, 5 is just, there's just 5. So it's just 1, 2, 3, 4, 5. We're at up here. This is n times 0.5 to find the position of the median. That's at, you could also do n times 1/2, because the median is 1/2 of the way through the data. Finally, step 6, square root. The square root of 40 is 6.32, we'll go with. That is our standard deviation. Remember we said for standard deviation, you go 2 digits beyond the data. The data here goes to the nearest whole number, or the nearest ones. So we go to the 2 digits past that would be the nearest hundredths. So 6.32 is our standard deviation. We've already found the variance of 40. How do we find the mid-range? Yeah, the max minus the min. Oops, sorry, plus the min, sorry, divided by 2. 26 plus 9 is 35, divided by 2 is 17.5. Bless you. Now, we found in this data, we didn't have a mode, but we have a median of 15 and a mean of 16. We said normally distributed, that bell-shaped curve, if it were perfect, perfectly symmetrical, that the mean and the median would be the same number. The fact that they're slightly different means that this is not perfectly symmetrical. Remember, the term we used was skewed. We're always skewed to the direction that the mean is going in. So skewed means it's stretched out. So this is, I may have exaggerated that skew a little bit, but what this is saying is this is stretched out to the right. The median is 15, that's somewhere in here. The mean is 16. It's always stretched out in the direction of the mean if the two aren't equal. So a question for you, which is a better measure of center? The mean or the median? Most people pick the mean because it's just satisfying. We add them up and we divide by it, right? It's an average. We've been calculating the average for a long time. And most people do pick the mean. But I'm going to give you an example here. In I believe it was 1984. 1984 or 1983. We're going to say 1984. University of Virginia. advertised that the average starting salary of a BA marketing graduate was just under $78,000 per year. 1984. Yeah, that'd be a really good starting salary right now. You offer me 78,000 right now, you might not see me here next week. If you look back at 1984, the average high school teacher was starting at like 16 to 17,000. That was really good money. That statistic was absolutely true. What they failed to disclose, one of the graduates who actually did graduate with a degree in marketing that year was a person by the name of Ralph Sampson. Most of you probably aren't old enough to remember, but Mr. Sampson was 7'4" tall and was the two-time NCAA basketball player of the year. Was drafted number 1 by the Houston Rockets. In the early 1980s, professional basketball was the highest paid sport in the United States. So Mr. Sampson had a multi-million-dollar contract as the number 1 draft choice. We're not talking just first round, we're talking number 1 overall draft choice. It takes a lot of $20,000 a year marketing graduates to average one multi-million-dollar contract down to $78,000. Mr. Sampson was the only person to graduate that year that made more than the $78,000. In fact, he was the only person to graduate to make more than $33,000 that year. That was a mean. The median income of that group was $24,000. The median is, accuracy is kind of a relative term. It's what we call stable. The median is more stable. One large number can change the mean because we add them up and divide. We're adding that one large number in there and we're still only dividing by one more. The median, the most it's going to do, since we just find the middle number, let's say that's our median right now, right? If we put in one more number that's really large, the most it's going to do is shift that median over a notch or half a notch to the next number up the list. So one really large, or the opposite, you can have one really small number is only going to pull the median one notch. But you can see an example like this, if it's extreme enough, it can pull the mean all the way outside of the rest of the data. In statistical analysis, a lot of times what they'll do is they will take something like Mr. Sampson's salary and they'll call it what's called an outlier. And they'll remove it from the data set, just make a little note for it at the bottom of the table or page or whatever saying this number was removed because it skewed the data, yeah. Okay, so we have all these measures of center and measures of dispersion. What are they good for? Well, one of the big things we can use, we can look at this bell curve again. Remember, the center of that bell curve is either the mean or the median or the mode. We're going to use the mean. So that is our mean, is the center of that curve. The standard deviation is a calculation of, on average, how far each number in the set is away from the mean. But it also has another significance. We can go out away from the mean in either direction in steps equal to a standard deviation. So what does that mean is if I subtract the standard deviation from the mean, I go one step below. That's -1 standard deviation. If I subtract another standard deviation, that's -2 standard deviations. I subtract a third one, that's -3 standard deviations. And I can do the same going the other way. I can add the standard deviation to the mean. Gives me +1 standard deviation. I can add it again to get +2. Add it a third time to get +3. So you might be looking at this right now saying, okay, why? Well, each of these little sections on this bell curve now have predictable percentages. Between the mean and one standard deviation less than the mean, 34.13% of the data will fall in that range. On the other side, between the mean and one standard deviation above the mean, another 34.13% of the data falls in that range. Between 1 and 2 standard deviations from the mean, 13.59% on either side. Between 2 and 3 standard deviations is 2.15% on either side. And outside of 3 standard deviations is only 0.13%. If you ever did like a Six Sigma training, yes, this is exactly what that's based off of. These percents that I just put in here are constant. They are always the same. Now, Six Sigma rounds them to 68, 95, and 99.7 rather than having the exact numbers in like this. So those percents always stay the same. What changes are the numbers that end up on bottom depending on what the mean and standard deviation of the data set is. For example, let's say that I take test one, not just from this class, but test one from every class I've ever had that took this style of a first test for business math. And let's say that of those students, there's a mean score of 78 with a standard deviation of 7. What does that mean? Well, that means that the center of this curve is 78 points. What's going to go down here in this next position? 71. Where did I come up with 71? Well, I took the mean of 78 and I subtracted a standard deviation of 7. The next position is going to be 64. I take 71 and I subtract that 7 again. So what's going to be the next one down here? 64 minus another 7 would be 57. Each step is going down by 1 standard deviation. The standard deviation here is 7. So each step is subtracting 7. If I go the other direction, each step is going to be adding the standard deviation, adding 7. So 78 plus 7 gives me 85. Going another step, 85 plus another 7 is 92. And then the last step here is 99. So if I ask, what percent of students would you expect to score between 71 and 92. Well, here's 71 right here. This is 92. If I add up those percents, I get, was it 68.26, 81.85%, it looks like. If I add up those 3% there. I might ask, what percent of students would you expect to score greater than 92? Well, here's 92. What's that? 2.28. I just add up those 2%, the 2.15 and the 0.13. Or we might ask, what percent would you expect to score less than 71%? Well, here's 71, less is these percents. If I add those all up, it's going to be 15.87%. You guys see the pattern? So we can find some rough percents, probabilities, if you will, make some predictions on how scores are going to come. Now, what has happened is we've had a lot of people take this test. We've had a lot of data that came up with this mean and standard deviation so we can make this curve. And we would expect now as more people take it, they're going to fall in those percentages, in those slots. Let's look at an example of how this could be useful to you. Let's say that you are looking to buy a new home. And you are right now, okay? So you do some research. And you find out, and this number was accurate as of about 3 years ago, that the mean selling price of a home, let's say you're looking for a 3-bedroom, 2-bathroom. So the mean selling price of a 3-bedroom, 2-bathroom home in the area that you're looking is 112,000. With a standard deviation of 21,000. So what that's telling us is the middle of this curve is 112,000. I'm just going to write 112. The next step is 91. How did I get the 91? Yeah, 112,000 minus 21,000. Next step is going to be 70, and the next step will be 49,000 minus another 21,000. Going up, we would have 133,000, the 112 plus a standard deviation of 21,000. Next would be 154, and finally 175,000. So these numbers down here came from the mean and standard deviation. Any questions on where those numbers on the bottom of the curve came from? Okay. Now the percents inside the curve never changed. So once again, this is 34.13%, 34.13%, 13.59%, 13.59%, 2.15%, 2.15%, and 0.13%. You find a house that you absolutely love, priced at $154,000. Your realtor is telling you, you better put in an offer right now and maybe put in an offer above the asking price because this one's going to go fast. Well, let's look at the data here. Here's $154,000, right? If I add those two percentages up, that's 2.28%. Yeah, only 2.28% of the houses in the 3-bedroom, 2-bathroom class are asking a higher price than what you got there. Or the other way to look at it is, if you add together these percents, that is 97.72% of houses in that 3-bedroom, 2-bathroom class are asking less than that price. So there's a pretty good chance you're going to find another house that's cheaper that you still like. Now, the weakness of this right here, of the whole, this is called the empirical rule. The weakness of this in the bell curve is we really need numbers that fall right on one of these standard deviation increments, right? I mean, we might even ask if 250 houses are up for sale in the area. How many would you expect to be priced between $70,000 and $133,000? Well, here's 70,000, here's 133,000. If we add up those 3% in there, 34.13 plus 34.13 plus 13.59, that is 81.85%. So now then we need to find that percent of the 250 houses up for sale. 81.85 over 100 equals blank over 250. We'll cross multiply and divide. 81.85 times 250 divided by 100. Oops. I'll just move the decimal. We get 204.6. So that comes out to be. So 204 to 205 houses. We would round that to 205 houses. We would expect there to be 205 out of those 250 houses priced between 70,000 and 133,000, just because of the mean and standard deviation. So anytime you're dealing with something that is approximately normally distributed, these percents will apply. However, like I said, even in this last problem, we saw that our numbers had to be right on one of these standard deviation steps in order to be able to use it. Now, you could fudge in between a little bit, I suppose. If you had a house that was 140,000, that'd be right in here. I suppose you could say, well, we know that it's at least 85% or so that are less than that, but you can't get a really precise number. You can still use it for kind of taking a guess at things and analyzing stuff, but you don't get exact numbers off of it. So another tool that can be used using the mean and standard deviation to compare numbers is something called the Z-score. Now, a Z-score not only compares things to their own standard deviation or to their own mean using the standard deviation, it can also be used to compare numbers from two different data sets. What a Z-score is, the Z-score of a number is equal to that number minus the mean for its data set. Then you take that difference divided by the standard deviation. So if you have the number 85 from a set that has a mean of 93 and standard deviation of 4, the z-score of that 85 is going to be found by taking 85 minus 93 and dividing that difference by 4. Well, 85 minus 93 is a negative 8, divided by 4 is negative 2. The z-score is negative 2. What that means, the negative means that it is below the mean. Less than the mean. So negative 2 is the number of standard deviations. So that is saying this is 2 standard deviations below or less than the mean. Well, why is that good information to have? Well, we could take that back up to our bell curve up here again and say, okay, 2 standard deviations below the mean, that's right in here. And we could look at those percents. But the z-score is really more powerful in comparing two things from different populations. For example, many of you had to take placement tests to come in here. Let's say you took a math test and an English test. And let's say that on that math test, you scored 56. And on the English test, you scored 68. Does that mean you're better at English than you are at math? Not necessarily. The math test may have been more difficult, or the English test may have been scored differently. So what we need to do in order to compare those two scores is we need to compare each of them back to their own population and see how they rate. And the z-score is the tool that we use to do that. So let's say that for the math test, we have a mean of 52 and a standard deviation, let me just do this, of 3. For the English test, let's say that there is a mean of 60 and a standard deviation of 5. Now you might still be tempted to look at that and say, hey, here I only scored 4 points above the mean. Here I scored 8 points above the mean. That's got to be more significant. Well, again, not necessarily. Let's do the z-score for each. For the math test, our z-score is our score of 56 minus the mean of 52 and divided by 3. Well, 56 minus 52 is 4. Divided by 3 is 1.33. That's saying that that score, your math score, is 1.33 standard deviations above the mean for everybody who took that test. Your English score, your z-score there would be the score of 68 minus the mean of 60 divided by the standard deviation of 5. Well, 68 minus 60 is 8. Divided by 5 is 1.6. That's saying your English score is 1.6 standard deviations above the mean. So yes, you did, when compared to its own population, you probably did score better on that English test than you did on the math test. So let's say you have 2 job offers. They are in different cities. The job offer in city A has a starting salary of $18.20 an hour, or starting wage, I should say, $18.20. The offer in City B has a starting wage of $16.70 per hour. Does that mean you should go for the offer in City A? No. There's cost of living considerations to take into place. Now, you can't just compare this wage to all wages in that area because you're just starting out. You have to compare apples to apples. So what you need to do is compare it to all other starting wages in each area. So let's say that in City A, the mean starting wage is $15.40 an hour. With a standard deviation of $1.50 an hour. In City B, the mean starting wage. I should probably specify in similar fields to the one you're in. You don't want to compare somebody going in as an accountant to somebody who's working fast food or working as an attendant at a gas station or something like that. They're not a fair comparison. But let's say in City B, the mean starting wage for people in that related field is $15.10 per hour with a standard deviation of 80 cents per hour. Let's find some Z-scores. So for City A, how do we set up the Z-score? 1820 minus 1640, you got it, over 150. 1820 minus 1640 is 180 over 150, which is 1.2 Z-score. 1.2 standard deviations above the mean. Over here on the right side, how do we find your Z-score? Perfect. 1670 minus 1510 over 80 cents. Bless you. So we subtract there, that is $1.60 over 80. That's two standard deviations above the mean. So assuming that the starting wages are a reflection of cost of living in those cities, your offer in City B is a way better offer. Any questions? Okay, I'm going to pose a question then for you guys. You are a manager of a department store. You have been told you need to get rid of, well, you've decided you're going to get rid of one salesperson. You have it narrowed down to 2 salespeople that you're going to get rid of. You have Taylor and you have Alex. You have decided you are going to let next week's sales decide which one goes out the door. Whoever does worse goes bye-bye. What's that? Well, hey, they've probably got a streak of incidences that would probably warrant. Let's say that Taylor here next week has sales of $2,700. Alex has sales of $1,400. Does this mean Alex goes bye-bye? Not necessarily. Let's say that Taylor here is in electronics. And Alex is in toys. Now, depending on the time of year, if it's not Christmas, generally you make more sales in electronics than you do in toys. So let's say that of all salespeople in electronics, The mean sales was $4,100 with a standard deviation of $500. Let's say for all the people in the toy department, the mean sales was $2,400 with a standard deviation of $400. I'm going to give you guys a couple minutes to figure out who would you fire. We'll come back from break at 6:30 and we'll go over this one. So on this one, we got to find our Z-score. For Taylor, it's going to be 2,700 minus the mean of 4,100 divided by 500. If we subtract 27 minus 41 is a negative 1,400. Divided by 500 is a negative 2.8. Taylor is 2.8 standard deviations below the mean. Alex, the Z-score there. 1,400 minus 2,400 over 400. That's a negative 1,000 over 400 equals a negative 2.5. Alex is only 2.5 standard deviations below the mean. So the one getting fired is going to be Taylor. Now, like I mentioned on break to some of you, a lot of your business management models, you're always looking to replace your worst employees. So I may have just fired Taylor, but Alex is probably not safe. I'm probably looking to hire somebody to replace Alex with as soon as I can find somebody that I think might be better. Okay, so that's the Z-score. That's how all this stuff of mean and standard deviation can be used to help analyze and predict situations. There are a lot more advanced methods that can be used using those tools to make those predictions and stuff like that, but that's beyond the scope of this course. More than what we can squeeze into a 2-week statistics unit. So we are going to move on. The next thing we want to talk about is measures of position. Measures of position mean not only, we talked about the curve. The center is where is the center of the curve, and the spread was how wide is the curve. Position is we're looking at a single piece of data. One single number in most cases, and finding out where is it relative to the rest. Now, a Z-score is a form of position. The Z-score tells us we're, the last example there, 2.5 standard deviations below the mean. That is a form of measuring position. But the Z-score is generally used to compare between populations. A more common measure of position is something called a percentile. Pretty much all of you, I'm sure, have heard the word percentile, whether it's you took a test and you're told you scored in the 63rd percentile, or you have a kid and you're told your kid's height is in the 82nd percentile for his age group, or whatever. What does that mean? Well, the percentile means what percent of all items in that group, in that population, have a smaller value. So let's say you take a test and you're told you scored in the 67th percentile. Is that a good or a bad score? We might say 67%. That's a horrible score. But remember, what that is saying is you scored better than 67%, right, of the people. If you were like absolutely average Joe, right in the middle of the group, where would you expect your percentile to be? 50%. Middle would be 50%, right? Half are worse than you, half are better, right? Well, on anything, any percentile, the 50th percentile is dead in the middle. That's average person. It's 50th percentile. So here, scoring 67th percentile means you're better than average. So, yeah, so that's actually a pretty decent ranking. Let's say that your child's height, they tell you that your child is in the 98th percentile for height for their age group. What does that mean? Well, that means that they're one of the tallest. That means only 2% are taller, or 98% are shorter in that age group. So that means your child is one of the tallest individuals in that age group. Let's say that you're analyzed on your job and your productivity. Puts you in the 46th percentile. Is that horrible? Yeah, it's slightly below average, but the law of statistics is half the people are above average, half the people are below average. So 80th percentile? Yeah, it depends on what they're comparing it against, though. If they're comparing it internally, that means you're only keeping 20% of your employees. Only 20% of your employees are meeting standard. Yeah, it has to be for performance. They usually measure you against an industrial standard, but not an industrial average. Yep. An industrial average means it's all the people working in that industry, what their performance is. So, I mean, 50th percentile would be half of the people in the industry are below that and half are above it. 80th percentile would mean only 20% are above it, so that's 80% that are unacceptable. So that's so they're looking at goals. They're looking at industrial standard. So you have to hit 80% of an industrial standard, which is a benchmark goal that's set, not what's actually being performed. There's a slight difference there. That's a very good point, though. It's a very good point there, though. It's they require you to hit 80th percentile on your goals or on an industrial standard. That's not actually what people in the industry are performing. Yeah. Well, I mean, they've set a standard at some point that this is the goal people are going to shoot for, and you better hit the 80th percentile on that goal. Okay, so let's look at calculating percentiles. Now, one of the things that must be done for percentiles is the data has to be put in order. To make our life easier, I'm going to make this data set in order from smallest to largest to begin with, so that we don't have to work on that. Now, I'm going to put it down at the bottom of the page. The only reason for that is so that I can do some work above it and some work below it, and so I don't have to rewrite the data set over and over again. So I'm just leaving myself some room here. So let's say the data set I'm looking at here are some productivity values. I have a 27, a 31, 33, 34, 36, 36, 39, 40, 45, 49. What do I have there? 1, 2, 3, 4, 5. We'll go 53 and 61. Those are my values. First thing I'm going to look at there is n equals what? 12. There are 12 items in that list. If I want to find the number, now this is a very small data set. Usually if we're dealing with percentiles, we're dealing with a data set with hundreds of numbers in it. To make it simpler, we're dealing with a data set with 12 numbers in it. So some of our calculations are going to be a little rough, but the process is still the same. So if I ask you to find the 80th percentile, the process for doing that, just like with median, one is to put them in order. We already did that. 2, find the position. To find the position, we take n times the percentile. 80th percentile as a decimal is 0.8. So here, n of 12 times 0.8 is 9.6. Now, just like with the median, if that comes out to a decimal, we do what with it? Round up. Even if that was 9.1, we would round up. So that would be the 10th position. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. The 10th position is the number 49. So 49 is the 10th percent or the 80th percentile for that data set. Find the 25th percentile. So that position, it's going to be n of 12 times what? 0.25, which gives us 3. Just like with the median, if that's a whole number, it's going to be between that place, the 3rd place, and the next one, the 4th place. So 3 and 4, that's 30 and 34, or 33 and 34, I should say. 33 plus 34 divided by 2 is 33.5. 33.5 is the 25th percentile. Because this came out to 3, an exact number, a whole number. If it's a whole number, it's between that position and the next one. If it's a decimal, you just round up and that's the position. Yes, always round up. Even if it was 9.1, you'd go up to the 10th number. That's fine. Yep. Because this is a small data set, by the way, the 10th number is the 80th percentile, but it's also probably the 78th percentile and the 79th percentile and the 81st percentile. You know what I mean? Because there's only 12 numbers, so if there were 300 numbers, well, then each number would be in its own percent. There'd actually be 3 numbers in each percentile. Yeah. So find the 35th percentile. And find the 75th percentile. I'm going to let you find these in your notes and we'll talk about them in a couple minutes. Okay, so for the first one here, it's going to be n of 12 times 0.35. What's that give us? 4.2, which means we round that up to the 5th place, which is 36. So 36 is the 35th percentile. For the next one down here, 75th percentile is going to be 12 times 0.75, which is 9. Since that is a whole number, it's between the 9th and the 10th. So it's between 45 and 49. 45 plus 49 divided by 2 is 47. Now remember, if you're punching this in your calculator, you do 45 plus 49, hit equals, and then divide it by 2. Otherwise, it tries to tell you something like 67 or 68, something like that. 69.5. Yes. Because that's a decimal, we round up to 5, yes. Even if it's 4.1, we round up. We can't just take 45, because remember, we have to have at least that percent of the data smaller than it. So 9 of them would be 75% of the data. So we got to be bigger than that. Yeah. So now what if I want to find the percentile of a given number? What if I ask what percentile is the 39? Well, to find the percentile from the number in where it is in the set, the percentile is the number that are smaller plus 1/2 times the number that are equal divided by n. So if I look at this, for 39, how many numbers in this set are smaller than 39? There's 6. Plus 1/2 times, how many numbers in that set are equal to 39? Just the one, just with 39. Over n, of course, is 12. So we do order of operations here. 1/2 times 1 is just 1/2. 6 plus 1/2 is 6.5 divided by 12. 6.5 divided by 12 is 0.5417, which is the 54th percentile. You might go 54.2 percentile or whatever, depending on what you're asked around. In this data set, what percentile is 36? How many numbers in this set are smaller than 36? There's 4 of them, right? Plus 1/2 times, how many are equal to 36? 2 over n is still 12. So 1/2 times 2 is 1. 4 plus 1 is 5 over 12, which is 0.4167, right? 1666666. So that would round up to the 42nd, we'll call it, just the 42nd percentile. What do you think? No? You do see percentiles a lot. So in your notes, what percentile is the 53? And what percentile is the 31? Okay, so for the first one, how many are smaller than 53? 10. How many are equal to 53? Only one. So that comes out to 10.5 over 12, right? What's that? 87.5. You are correct. 0.875. So that 87th, 88th percentile or 87.5th percentile is fine. And then for the last one, how many are smaller than 31? 1, right? How many are equal to 31? 1, and that's still over 12. So that's 1.5 over 12, or 0.125, which is your 12.5%, 12.5%. If you rounded that to the 13th or whatever, that's fine as well. Unless stated, yes, you can round however you want to. Okay, our next little topic here. This is one of those, we're going to cover just a little bit of the topic. It could be as big as we wanted it to be. I mean, statistics is one of those topics I could honestly go on for at least 2 semesters, if not more, just because there's that much material in it. To me, statistics is probably the most important topic you can learn. You can go through your whole life not seeing any statistics around you, but once you've learned about statistics and know what they are and how they work, you see them everywhere. Everything in business is about statistics. Employee evaluation, as we've mentioned, market analysis, deciding whether to try a new product or a new process. It's all about statistics. What do you charge for a product? It's all about statistics. Most of your managers, your CEOs and CFOs in companies have 2 things. 1, a background in accounting, and 2, a background in statistics. So the little section of statistics we're going to cover now is probability. Probability is, quite simply put, how likely it is that something will happen, will occur. Now, how likely it is that something will occur implies that it has not happened yet. And that is absolutely true. If it has already happened, probability doesn't apply to it anymore. Probability is about predicting future. Of course, it's predicting future based on the past. Now, there are a couple of different types of probability. There's a relative frequency probability. Relative frequency probability is probably the most common probability used in industry because it's the easiest one to get information on. So let's say that each year out of 48,000 drivers in the first year of their license. So in other words, that's most likely 16-year-olds just got their driver's license. $5,200 will be in accidents. So what this is telling us, based on past experience over the past several years, there's about 48,000 new drivers every year. And of those 48,000, about 5,200 of them have accidents in that first year. So the probability of a new driver having an accident in their first year is just that rate of 5,200 out of 48,000. So 0.1083. So that's the probability that a driver will have an accident in their first year. So just over 10%, almost 11%, will have an accident in their first year. That's probably even a little bit of a low number, by the way. No, you got a 16-year-old coming up. They've seriously restricted, of course, the 16, which I'm sure you've seen that they've really restricted the 16-year-old drivers. Like nighttime driving is restricted, and how many people can be in the car and all that stuff. So it's way different than when we were there. You got your driver's license. Hey, you've got full privileges. Go to it. Yeah. The second I got my driver's license, I had 3 or 4 friends in the car with me at all times because they didn't have their license. I drove a car that had that, but that wasn't one I owned. Although driver's ed was the first time I had driven a vehicle with automatic transmission. That's just because my dad was stubborn. Everything my dad drove was stick shift. Yeah. Good luck finding one nowadays. Even a truck, it's hard to find stick shift in. Yeah. Really? It's. I like stick shift, but I mean for city driving, I do get the manual transmission. Anyway, so that's relative frequency, sometimes called empirical probabilities. That is probably, like I said, industrially, the most common way probabilities are calculated. For our purposes here, we're going to stick to a little bit simpler. We're going to use some of that relative frequency later on when we look at contingency tables and those probabilities. But we're going to start out now looking at simply what's called theoretical probability. And theoretical probability basically just goes off of counting the possibilities. Everything we do is an experiment. Every experiment has outcomes or results. The results, so we have an experiment, and those experiments have results. Those results can be divided into either successful or not successful. We could say success and failure, but that's just not a nice way to put it. What do I mean by that? We roll a die. That's our experiment. We're rolling a die. What are the possible results? Yeah, 1, 2, 3, 4, 5, 6. 1 through 6. What if I want to know The successful results or outcomes are the ones that answer our question or meet our condition that we've met. So what is the probability of rolling a 4? Well, how many 4s are there? 1. How many total possibilities are there? 6. 1 out of 6, or 0.1667. Standard, by the way, for probabilities is 4 decimal places usually, unless otherwise stated. So theoretical probability is the number of successful results over the total number of results. There were 6 total results, but only one of them successfully met the condition we were looking to have. What if we ask, what is the probability of rolling an even number? How many even numbers are there? There's 3 out of 6, or 0.5. Well, if we're just dealing with rolling a die, yes. That's a good question. Why is it always 1 through 6? Well, let's look at other possibilities. On a die, there's only possibilities. Flipping a coin. Now I'm going to do some notation here. P is saying what is the probability of, what goes inside here is the result. What's the probability of getting heads? Well, how many heads are there on a coin? 1. How many possible results are there? 2. Now, I always get somebody says, well, what if the coin lands on edge? That is such a minuscule possibility that it's not worth considering. I mean, it's like a 1 in a million chance. So it's just too small to consider. So that's a 1 out of 5 or 50%, or 0.5 probability. Now, that's not exactly true. That's if it's what we call a fair coin. If you're looking at standard government minted coins, they are not fair coins. What's that? They're always heavier on one side and the shape on one side. Usually they're more likely to land heads up because the head side sticks out further. So it's more likely that they hit that side, they'll bounce over instead of landing flat. And it's usually right around 51 to 53% heads versus, 47 to 49% tails. So if you ever have a kid that you need to discipline and you want to teach them something at the same time, give them the option of being grounded for a week or go in the other room and flip a quarter 1,000 times and record the results. No, I haven't. My kids have been fairly good. But yeah, it actually does come out to be, and of course now if you actually flip the coin and counted, that would be a relative frequency probability because it's how many times it actually came up heads out of how many times you flipped it. And usually that relative frequency probability is usually more accurate. It accounts for all those little nuances that the theoretical does. Yes. Yes. Yeah, the more times you do it, the more accurate that relative frequency probability is. If you only do it 100 times, it's not very accurate. Marbles in a box. Let's say we put in 30 red and 20 blue. We mix them all up good. What is the probability of reaching into that box and randomly drawing out a red marble? Well, there's 30 red ones out of 50 total, right? Remember, it's the successful ones, which would be the red ones, out of the total, which is everything added up. So that is 0.6 probability, or 30 out of 50. What's the probability of reaching in there and randomly pulling out a blue one? 20 out of 50, good. Or a 0.4. So those are simple probabilities. Now, let's look at something called compound. Don't need to know this term, but compound events. Compound events involve an experiment where more than one thing has to happen. I'm going to reach in there and I want to draw out 2 marbles. What is the probability that the first one will be red and the second one will be red? Well, for what I've given you here so far, we don't have enough information, because there are 2 possibilities here. There's a term called with replacement and without replacement. When we have 2 things that are going to happen here, we have to view one of them as happening first. So we'll view the first marble, the first red marble, is happening first. So whether we draw both marbles at once or just one at a time, it doesn't matter. One of them is first. There's a first marble. We look at that first marble and we see that it's red or blue or whatever. What do we do with it after that? Well, do we throw it away and then draw the second one? That would be without replacement. Or do we look at it, record whether it's red or blue, and then put it back in the box, mix it back up before we draw the second one? That would be with replacement. What's the difference? Well, yeah, the probability changes or doesn't change. With replacement, the probability of the first one being red is 30 out of 50. If I put it back before I draw the other one, the probability of the second one being red is still 30 out of 50. That's 900 out of 2,500, or 0.36 probability. Without replacement, well, the probability of the first one being red is still 30 out of 50. But if I don't put that back, if I throw it away, the second probability, now there's how many red ones? 29 out of 49. So that is, oops, all right. Oh, let's try that again. There we go. 0.355. 0.3551 instead of 0.36 probability. Now you might ask, well, how did we know the first one was red over here? Well, because if it wasn't red, we don't care anymore, do we? If it's not red, we're not going to get both of them red. So if the first one's blue, which is possible, we're done. We don't have to calculate anymore. So the only reason we would ever calculate the second one is if we assume the first one was red. Because we drew it out, the first one was red. The chances of the first one being red are 30 over 50, right? We draw it out, it's red, we throw it away. It's gone, it's not in the box anymore. Now we've lost one, so there's only 29 red marbles in there and 49 total. Does that make sense? So the probability of the second one being red is 29 out of 49. This second probability here, with replacement, well, the marbles are in the box, right? We reach in, we want to draw 2 red ones. We reach in, we grab one, we look at it, it's red. Before we go for the second one, we put it back in and mix them back up. So still the whole 50 are in there. Yeah. This second probability here is what's called a conditional probability. That's the probability of the second one being red. The probability of the second one being red, given that the first was already red. Like I said, if the first one was blue, well, there's still 30 red ones in there out of 49, but we don't care about that case because we need both of them to be red. If I reach into the box and I grab 2 marbles at once, is that with replacement or without replacement? Yes, because the second marble was chosen before the first marble was put back. Does that make sense? It's kind of a weird thought. When would that ever be useful? Now we're going to make it so it applies to something that would be more useful. No, that's okay. So why would this be useful? Good question. I'm trying to come up with an example that's simple enough to understand. With 5 marbles? Well, let's get away from marbles and get something a little more meat and potatoes. Let's look at something called the contingency table. What a contingency table does is it compares 2 things. For example, let's look at a business and its employees. Let's say that in this business, you have 3 types of employees. You have hourly, salary, and commission. You want to look at how they do their health insurance. Do they take the company plan? Are they on a spouse's plan? Or do they just float with no insurance? So let's say that of our hourly employees, we have 142 that are on the company plan. We have 49 that are on a spouse's plan. And we have 9 that just choose not to have insurance at all. For those that are on salary, we have 26 that are on the company plan. We have 10 that are on the spouse's plan and 4 that choose to say, no way. For those who are on commission, we have 2 that are on the company plan, 1 that's on a spousal plan, and 2 that say, nope. So we want to analyze some probabilities here. To do probabilities, we need totals in both directions. So we need the totals of the rows. Our row totals here, 142 plus 49 plus 9 is 200. I might have. For salary, that row total, 26 plus 10 plus 4 is 40. And for commission, 2 plus 1 plus 2 is 5. We also need the column totals. For the company plan, we add those up. 142 plus 26 plus 2 is 170. Spousal plan, 49 plus 10 plus 1 is 60. And no insurance, 9 plus 4 plus 2 is 15. Now there has to be a grand total here. It better be the same in both directions. 200 plus 40 plus 5 is 245. Well, 170 plus 60 plus 15 is also 245. So just a way to double check. This table is a contingency table. All it does is it compares two values, two things. Two variables is the technical term. So one variable is the type of class of employee, hourly, commission, and salary. The other variable is their type of insurance. So now we're asking the question, what is the probability that a randomly selected employee let's just say, what is the probability the randomly selected employee is on salary? Well, we can look at this table and very quickly figure out how many are on salary. 40. Out of how many total? 245. So that's 40 over 245. 0.1633. Or 16.33% if you want to do it as a percent. No, that's fine. Number two, what is the probability that a randomly selected employee is on a spouse's plan? Well, how many are in a spousal plan? 60, right? Out of 245. So 60 divided by 245 is 0.2449. Yeah, so 24.5% basically. So if you look at this, it's telling us your employees are more likely to be on a spousal plan than they are to be on salary. Now that's not terribly useful information, but as we progress with this and analyze it a little bit deeper, we are going to find information that could be pretty useful. The third thing I'm going to ask, what is the probability a randomly selected employee is company plan and hourly? So we've got that and in there. What does that mean? Yeah, it has to meet both conditions. Our company and hourly. Company plan is this right here, right? Hourly is right here. What part of that meets both conditions? The 142 does. So there's 142 that meet both conditions out of the total of 245. So that's 0.5800. Nope, it was just these 142 here that were in both. That's both hourly and company plan. Yep. So how would that be different, which is getting to what you were asking, if we said on a company plan or hourly? Now, to meet that condition, they only have to meet one of two. They're either on the company plan, which is that yellow column, or they're hourly, which is the yellow row. So we could add up all of those. If it meets any one of them, they're meeting that. So it could be 142 plus 49 plus 9 plus 26 plus 2. All of those highlighted numbers. divided by 245. We're still looking at the whole group of 245. Well, if we look at that, what is that going to give us? Was it 228 out of 245, I believe? .9306. What's that? Oh, I might have screwed up my adding there. Let's see there. No, it's 228 over 245. Let's see if I punched it right. Try her again. See if you come up with my number. Okay. .9306. Okay. Is there a shorter way we could have come up with that? Well, the answer, if I'm asking, there probably is. I look at the total for hourly, that is 200, right? I look at the total for company plan, that's 170. Now that would add up to 370, that's way more than the 228. Why is that more than the 228? Yeah, the 142 is counted twice. It's in both the row and the column. So we have to subtract out the one that's counted twice. That would give us 228. In fact, that's how I added them up. Instead of adding the 5 numbers, I added the 2 and subtracted the 142. So that's the difference between the ands and the ors. I've gone way long, by the way, on our break. So let's take our break quick and we'll come back and talk about these more. It is 7:26. Let's come back at 7:36. So we said this gets more complex. How can it get more complex? Well, we talked about those conditional probabilities before where we calculated a probability on the knowledge that something has already occurred. So let's say here, I don't know why I said 3 again there. Turn my pen on. So let's say here we are going to calculate the probability that a randomly selected employee is on a spousal plan given that they are salary. The word given means we know something about them. What comes after that word is what we already know. So what do we already know about this person? They're on salary. So what that's telling us is we're no longer looking at the whole 245 people anymore. We're only looking at the ones that are on salary, right? The 40 people on salary. How many of them are on the spouse's plan? 10. So what we're looking at there is the 10 that are on the spouse's plan out of the 40 that are salary, or a 0.25 probability. So now an interesting question. What is the probability that a randomly selected employee is on salary given that they're on the spouse's plan? Is that probability going to be the same? No. This time, what we know is that they're on the spouse's plan, which means, once again, we're not looking at the full 245. We're only looking at the ones on the spouse's plan, which are 60. Out of those 60, which ones are we concerned with? The 10 that are, there we go. We're concerned with the 10 that are salary. So we're looking at those 10 that are salary and spouse's plan out of the 60 that are on the spouse's plan, which is a 0.1667 probability. It's just the accepted standard for statistics, 4 digits on probabilities. So how is this yeah, usually 4 digits is what I expect. Or a percentage, yes. A percentage to 2 decimal places. So either 0.1667 or 16.67%. let's say we want to analyze what category is most likely to take our insurance plan. So in other words, we're looking at we're looking at three different probabilities here. One of them is the probability that they're on the company plan, given that they're hourly. The second one is the probability that they're on the company plan, given their salary. And then the final one that we're looking at is the company plan, given that they're on commission. So for the hourly, how many hourly employees are there? Well, there's 200 and 142 of them are on the plan, right? So that's 142 out of 200, or 0.71. For salary, there's 40 salaried employees, 26 are on the company plan. So 26 out of 40, or 0.65. Any questions on where those numbers came from? I know I went kind of fast there. Okay. The company plan, given that they're hourly. So I went up here and we said, okay, that means that we're only looking at the hourly employees now. There's 200 total, and 142 of them are on the company plan. So that was 142 out of 200. Then here for a given salary, now we're only looking at the ones that are on salary. So yes, that's the 26 out of 40. And then the last one, yes, for the commission, it's going to be 2 out of 5. There's 5 people on commission, and 2 of them are on the company plan. Come on, my computer's starting to get slow. So 2 out of 5 in the commission class are in the company plan, so only 0.4 or 40%. So what that is telling you is significantly less likely that somebody on commission is going to take the company insurance plan. Why would that be important news? Well, important information? Well, let's say we're looking to hire another employee that's going to be on commission. We have to plan our expenses, plan the cost of that employee. We're going to look at only a 40% chance that they're going to take the company insurance plan, so we're going to plan accordingly. There's a pretty good chance that they're not going to take our insurance plan, so we don't have to worry about that cost. Now, that doesn't mean we don't worry about it at all. We use it to weight. One of the cool things about probabilities, and this is beyond what I would ask you on a test, but that just kind of brought it. How do you weight that? There's a probability that's going to happen. So let's say you're looking at that. You want to look at the predicted expense. So let's say your employees, you're going to hire that commission employee. And let's say that of your current commission employee, say about 20% of them make $40,000. About 70% of them make $50,000 a year. And about 10% of them make $60,000. In other words, that's a 20% probability that this new person is going to make $40,000, 70% probability they're going to make $50,000, 10% they're going to make $60,000. So what do we expect to pay that person? Well, we do this. 40,000 times 20% is $8,000. 50,000 times 70% is $35,000. And 60,000 times 10% is $6,000. We add all those up and we get $49,000. So we would expect on average to pay anybody working for commission about $49,000. It's kind of like a weighted average. You could. Well, how then would you figure in that insurance? Let's say your insurance costs per employee costs $15,000 a year. We said there's only a 40% chance that a commissioned employee takes the insurance. So 40% of that is $6,000. So we would add, okay, there's another, that raises that total expected cost up to around $54,000 for that employee. Then there might be other benefits that you do the same analysis. This classification of employee only has a certain percentage of earning this benefit or taking this benefit, and so on. Company car, yes, and all that stuff can come in there. Commission often is salespersons. Bless you. So it all depends on whether they're in-house sales or whether they're in-person sales. So you got to send them out there. Oh, yeah, you could. I'm going to propose a game to you. Cost to play the game is $20. If you win, you get $10,000. If you lose, you get nothing. Do you want to play? There you go. It depends on what's the probability of winning. What do you have to do? We're going to use, here's the game. We're going to use 2 decks of cards. To win the $10,000, the first deck, you have to draw a king. First deck, a full deck, 52 cards. You have to, yep, 1 draw. The second deck, you have to draw heart. Well, what is the probability of drawing a king? How many kings are there? 4 out of, well, but this is only 1 deck. This is the first deck, right? So there's only 4 kings out of 52 cards. 4 divided by 52 is 0.0769. Yep. How about the hearts? How many hearts are there? 13, right? Ace through king out of 52. Yes. So 0.25 is that probability. So what's the probability of getting both to happen on 2 consecutive decks? That's why I used 2 separate decks, so that the first one didn't matter, right? Didn't matter if it was the king of hearts or not. We multiply those together. 0.769 times 0.25 gives the probability of 0.0192. That's your chance to win. So what that's saying is up here, there is a 0.0192 chance that you're going to win $10,000 and a 0.9808 chance of getting nothing. Where'd the 0.9808 come from? Yeah, that's the rest. It's just 1 minus the 0.0192, 100% minus the 1.92%. Right? Well, 0 times anything is 0. 10,000 times the 0.0192 is 19.2. Your estimated winnings, every time you play the game, on average, you're going to win $19.20. It costs you $20 to play, right? So on average, every time you play, you're going to lose 80 cents. At least you had fun. I don't go to. I know the probability, so I don't go to the casino very often. Now, this is how actually people hate shaking dice with me because they'll roll like 3 threes. Now, you're gonna stay with that? That's only a 48% shot to win. But so anyway, here, it costs you $20 to play. On average, you're going to win $19.20. That's actually pretty close to a fair game. A fair game would be it costs you $20 to play, and on average, you would win $20 a game. So this is how casinos do it. So it doesn't matter. The casino doesn't care whether you win or lose. They care that you play. Because on average, the casino is going to make 80 cents every time you play. You might win, but the guy next to you is going to lose big. Does that make sense? Okay. There is a new quiz due tomorrow, Thursday at 11:59 p.m. Because do homework due for next week, next Wednesday. Now, as I had mentioned before, we've got pretty poor timing set up here. We've got 2 more lectures, 2 more weeks of lecture in Unit 2. That'll be next week and the week after. The week following that is spring break. So we'll have a 2-week gap between the last lecture of Unit 2 and the Unit 2 test. Yes. Let me take a look at the table. They changed the numbering of the table of contents in this book. So let me just take a look at the table of contents. I can tell you quickly here. So obviously, the chapters they skip some chapters, but chapters 2, 3, 5, and 6 for Unit 1. So Unit 1 was 2, 3, 5, and 6. Unit 2 is 7, 8, 9. Yes. We've only done chapter 7 so far. We've got to do chapters 8 and 9 yet. And then Unit 3 is 11, 13, and 14. After 14, if you still survive. Yes. It's not that bad. I have never had somebody who well, actually, I should take that back. This is my 18th year here, and I've taught at least one section of this class every semester, so at least 36 to 40 sections of this class. I think I've had 2 people in that time that have actually showed up for class every week, did all their homework, and didn't pass. So the pass rate is very, very high. The ones who fail are the ones that disappear or stop doing their homework, or they did. And like I said, usually they did very well on the first test, so they say I can blow off to my math lab homework or something, and my math lab ends up being like 25% of your grade before it's all done. Still fail. Still get a D. Yeah. Okay. If you guys don't have any questions, you have a great week. Computer lab next door here is open if you want to work on anything. Otherwise, I will be in here with the network up until 8:20. or 8:15 if it's really quiet.